So 9.3, day 2, similar right triangles. We're just going to start with kind of recapping really quickly what we talked about on Friday with day 1 of this. There's a lot of words on this page, so I'll try to paraphrase as best as I can. We were given on Friday something that looked like this triangle here. If it'll let me draw this one in the middle, triangle ACB. Where'd it go? That's not what I wanted. All right. Technical difficulties. It always happens like as I'm, oh, here we go. Okay, so we were talking about this triangle here. And we said in that triangle, we can draw 3 similar triangles within that because we have the altitude CD here. So altitude CD gives us the ability to draw 3 similar triangles from that. We had kind of our triangle on the left side of our altitude, triangle ACD, and then the smaller triangle, triangle BDC, so this little sliver here, and then we have the full one, we have triangle ABC, so the largest of the 3. And we said they were similar, so we could set up proportionality statements. So that's what we have all over here. All of these are just proportionality statements between the 3 triangles. And what's on the bottom row here is us cross multiplying. So CD times CD is CD squared, and this is AD times BD. Same thing here, we have CB squared, this is DB times AB, AC squared, AD times AB. Which will lead us into, we talked about this too on Friday, the geometric mean. On Friday, we just kind of introduced it, just how we learned how to compute it or evaluate it. I didn't tell you what it was actually used for. But geometric mean was x squared is equal to our A term times our B term. And really, that's what we have in all of these in our bottom row. We have a term that is squared equal to an A term and a B term. So think A and B are just numbers, just like AD and AB are just numbers. So what similar triangles gives us the power to do is use these properties of geometric means to find different things. So we have 2 theorems that we're going to use today to use the geometric mean to find the altitude and also the length of a leg of one of the triangles. So the first one, geometric mean or altitude theorem. So the length of the altitude, so altitude is like your height of your triangle. So here altitude is CD. So the altitude is the geometric mean of the lengths of the 2 segments of the hypotenuse. So when we draw this altitude, we split our hypotenuse into 2 segments. We have a AD segment and a DB segment. So we can find the length of CD by saying, well, that's AD times BD, which this fits into our geometric mean theorem, which is x squared is equal to A times B, where we have kind of our x squared would be our CD, AD would be our A term, and BD would be our B term. So that's one of the theorems. I think this is the easier of the two. The second one, there's just some more vocabulary in there that we have to pay attention to. So our second one is the geometric mean, but now we're talking about the leg of a triangle. So the two legs of this right triangle would be CB and CA. Those are both legs of our triangle because AB is our hypotenuse. So again, with our altitude CD, our hypotenuse is broken up into two segments. We have A to D and B to D. And what our leg theorem says is that if we take the length of the leg squared, that's equal to the adjacent segment of our hypotenuse, so adjacent meaning next to, and then the length of the hypotenuse altogether. So we just look at CB here. So, okay, well this is length CB squared is equal to the hypotenuse, the segment of the hypotenuse that's adjacent, which meaning next to. So next to would just be DB. So that's why we have this DB here, times whatever the length of AB is. So a lot of the time to find the length of AB, we're going to have to add this red segment and the blue segment together to get our full length. And just like if we were looking at AC, the red segment of our hypotenuse is the one adjacent, so we take the length of AD times the full length of our hypotenuse. This one I think is a little more tricky just because there's kind of more vocab and parts, like I said. So when I use this theorem specifically, I'll make sure that I'm making that distinction as to when I'm using it and why I'm using it. All right, so a lot of words on the front, but not that bad. Let's look to the back, and I think we have 3 examples. Yeah, 1, 2, 3. Sweet. All right. Scroll down. All right, so for example 1, we're trying to find the value of each variable in this larger triangle here. It's kind of what we mean by a larger triangle. Our hypotenuse would be opposite of our right angle, so this is our hypotenuse. Let's label these vertices. I'm just to make it easier. You really don't have to, but instead of just pointing, I can explain now. And then this point is D. So our altitude is what we're trying to look for. We're trying to find whatever dB is. Well, if I use theorem, the first one that we had on our page 9.7, that's to find altitude. So I'm going to be using theorem 9.7. And that says if I take my altitude squared, so dB squared, that's equal to the two lengths, the two segments of my hypotenuse multiplied together. So dB squared is equal to AD times DC. From there, I have enough to plug in values now. We know dB is x, so this is x squared is equal to AD is 6 and DC is 3. And then now we kind of start the process of finding the geometric mean that we started to practice on Friday. We multiply our two numbers together, so you have x squared is equal to 18. And then you're going to want to take the square root of both sides, because we have to undo that square. So x is equal to, you want to write it as an exact answer. That would be 3 square root of 2 would be your exact answer, because 9 is the largest perfect square. That goes into 18. If you want to do a rounded answer to your first, to the 10th, you would get out 4.2. Again, this is just finding really what your geometric mean is. It really is just the square root of your two terms multiplied together. All right. So next example, example B, this time we're not asked to find our altitude. We're asked to find a leg. All right. Before I start again, I'm going to label my points A, B, my vertices A, B, C. Label this point D. So now we're going to be using that second theorem because now we're trying to find a leg. So this is theorem, the geometric mean, so the leg. So the second one on the first page. Where we could say, okay, well, our leg or our y squared, instead of y squared, let's put the side length in since I have them. AD, AB. AB squared is equal to the adjacent segment of our hypotenuse. So here's our hypotenuse. The segment that's adjacent to AB is BD. So I take BD times the length of this hypotenuse. So BC. All right, now we can go back and plug in. Like I said, AB was y, so we have y squared is equal to BD is 2. And the length of BC is 5 plus 2, so you get 7. So y squared is equal to 14. Got to take the square root of both sides. 14. There's not a perfect square that goes into 14, so you can't simplify it at all. You can just leave it as square root of 14 would be your exact answer. Your approximated answer to one decimal point would be 3.7. Last one, we're just going to do a word problem that kind of puts them all together. The setup goes, we're trying to build a rock wall in your high school gymnasium. We need to find the height of the gym wall. We use a cardboard square to line up the top and the bottom of the gym wall. Our friend measures the vertical distance from the ground to your eye and the horizontal distance from you to the gym wall. Approximate the height of the wall. So I can use this 8.5 and say, well, 8.5 squared, 8.5 is a altitude. I can say, well, that's equal to my two segments multiplied together. W times 5. So I can say 8.5 squared is equal to W times 5. And then if I take 8.5 squared, I would get out, what is it? 72.25 is equal to 5W. And then you divide each side by 5. So W is equal to 14.45. And then we want to find this total length. We have to add 5 to this. So the height of our gym wall is W plus 5, which is 19.45 feet would be your final answer. So the homework starts off just by doing some practicing with geometric means. Then there's just